IMPA, and he'll talk about some problems concerning germs of singular varieties.
Thank you. So, that's the abstract. Well, the problems I consider is mainly are mainly motivated by the following theorem. It's not very well because I divided. I'm not my experience in transparency is not very good, so that's the first time I give a talk with transparency. I forgot to divide here the page. So, Halford proved the following theorem in 19th century. Suppose that you have three polynomials satisfying three homogeneous polynomials in C2. No, it's wrong there. It's wrong. C2. No, in C3. That's correct. C3. Satisfying. No, C2. C2. Satisfying the relation like that. And such that the degrees are given P degree of F equals Q, degree of G equals R, degree of G. Then you have a relation like that, 1 over P plus 1 over Q plus 1 over R, bigger than 1. And moreover, for each solution of this inequality, then there are polynomials which satisfy the relation, and moreover, they are universal in the sense that any order can be written like that, okay? Like here, no? Any other solution can be written like that. This means that the polynomials big F, big G, and big H, in fact, they are a kind of universal covering of the surface. So you consider the surface, consider the surface, this surface, MPQR, no? Okay? And if you given by the relations, no? The map FGH from C2 to C3, if you consider from C2 minus 0 to MPQR minus 0, is the universal covering of the surface, no? Okay, that's remark 1. For each parameterization of MPQR, these parameterizations are related with the groups, finite groups of PSL2C, of homographies. And some of them are known by Euler, Hope, Liouville, and others, but the general case are found by Schwartz. And some explicit expressions can be found in this reference for the parameterization, for the universal cover. Now let me give so this theorem was my motivation, and I will give and so the problem I will study, the first problem I will study is when there is a parameterization from say Cn to a local parameterization from Cn to a surface with singularity, okay? Not necessarily with isolated singularity, okay? So that's the problem. So the definition. So the first theorem is when the surface is quasi-homogeneous. So in this definition, I define a quasi-homogeneous surface in general for. In fact, is a quasi-homogeneous surface is some surface which is tangent to some vector field. Okay, vector field here, such that the eigenvalues are rational and positive. Okay, so that's my definition for for the quasi-homogeneous surface. And the motivation is that when the surface is a hypersurface, for instance, then the condition that is quasi-homogeneous means that in fact it's quasi-homogeneous in the usual sense, no? Okay? So if the vector field is the radial vector field with all the lambda j's equal, then you have a homogeneous surface, okay? But in general, you have some weights for the the variables, okay? So that's the definition. The vector field must live invariant. The ideal defines the surface. Okay. A notation is the singular set of the variety, of the germ. In principle, I'm considering germs, no? And M star will be the complement of the singular set. And another motivation is this theorem by Saito. I think most of you know this theorem. It gives a sufficient condition for hypersurface to be quasi-homogeneous. Okay? So suppose the hypersurface is given by f equals 0, and suppose the surface is an isolated singularity at 0, and f belongs to its Jacobian ideal. Then f is quasi-homogeneous. You can say that f is quasi-homogeneous. There is a vector field like I defined. I gave in the definition. Okay. Another definition. So this definition, I consider a reducible subset, germ, in fact. I'll say that the dimension is less than equal to k if either the singular set is empty or all irreducible components have of the singular set have dimension less than equal to k. And the dimension will be k if the singular set is not empty and all irreducible components have dimension k. Okay? And another definition, I consider a map from, so the variety has dimension n, no? Pure dimension n. And I consider a map, a germ of map. And I say that phi minus 1 of p equals q. If there exists some representative of phi, such that satisfies this property, no? locally, okay? Okay, then now I state the results. The first result is about a quasi-homogeneous surface, but let me give another. So I consider the case complete intersection, okay, of a quasi-homogeneous surface defined by complete intersection, and quasi-homogeneous with respect to some vector field, okay. And since you have this condition, that exists a matrix U of functions, no? Such that we have this, okay? So the theorem 1 says that gives a necessary condition for the existence of a map. So suppose in the above situation, suppose that the dimension of singular set is less than or equal to n minus 2. So we are in Cn plus k, no? Cn plus k. But the dimension of the singular set is at most the dimension of the variety, minus 2. And there exists such a germ of a Lorentz map from Cn0 to M0, such that phi minus 1 of 0 is 0. Then the trace of the vector field is bigger than the real part of the trace of the matrix U at 0. Okay? So let me give a corollary here. For instance, if suppose that we have the matrix is diagonal, okay, and the LG here are rational positive, no? Of course, because in this case, they must be rational positive. And then the condition says that if there exists such a map, no, then the trace of the matrix of the vector field is bigger than the sum of the LG and J. And in the case of Halpern's theorem, the surface MPQR is quasi-homogeneous with respect to the vector field, this vector field, okay? Because it's XP, YQ, ZR, no? Quasi-homogeneous with respect to this vector field. So the condition, and this vector field satisfies X of F. F is equals F, no? Okay. X of, so the condition on the necessary condition says that exactly the conclusion of half, no? Okay. Okay. Bom, in the case n equals 2, k equals 1, M is not necessarily quasi-homogeneous a priori. We have a complete classification for the germs which admit parametrization, no, of this kind. So this is theorem 2. Suppose that we have a germ at 0 in C3 of hypersurface with an isolated singularity. And suppose there exists a germ of a Lorentz map with this property. Then M is equivalent to one of the following surface. there are the MPQR, no, and these values of PQR given there are the solutions of the inequality. One over these values, no, are the solutions of the inequality. 1 over P plus 1 over Q plus 1 over R bigger than 1. But there are other possibilities. Okay, there are other possibilities. And each one of these possibilities, they are covered, in fact, they are covered by some MPQR, okay? I don't remember now, but there is this, for each other possibility here, there is a map from some MPQR to here, which is a covering map, okay? And so this is a complete classification in the case of dimension 2, okay? N equals 2, K equals 1, no? Hypersurface in C3, but isolated singularity, okay? Well, and moreover, the surface in the above statement are 2 by 2 non-equivalent. It can be proved that they are non-equivalent because either the number, the fundamental group of the complement of 0 are different in each case, but it can, some of them you can distinguish by the Milnor number also, okay? Milnor number. Well, now another, this was a little bit surprising for me, this theorem 3. Suppose now that we are in dimension bigger, n bigger than equal to 3, so we are in dimension at least 4. And we have a germ, no, at 0. And suppose that the dimension of singular set is less than or equal to n minus 2. And there exists, not necessarily quasi-homogeneous, no? And there exists a germ of a holomorphic map with this property. Then, in fact, the dimension of the singular set is n minus 2. Okay? So it's not possible to find this type of thing, except for in n bigger than or equal to 3. It's not possible to find a parametrization, for instance, in the case of the surface x sum of squares. Okay? Sum of squares. There is no parametrization like that. Okay? Okay? Because in this case, the singularity is isolated, no? And this excludes the case of isolated singularity. Okay? So let me show. At the end, I'll give some problems related with these theorems and some other theorem I will state at the end. So in the proof, it is strongly used that in all cases we consider, in the case of singularity of a complete intersection, okay? We use that there exists an n form, non-vanished n form in the m star, okay? And this is n form. It can be defined as consider the. Let me sketch the definition of the n form. Okay. So the n form is defined only in the surface m star. Okay. It cannot be extended to the whole space unless the surface is non-singular, okay? So consider the K-form, theta, big theta, the F1 wedge, the Fk. And so it can be written like that, no, it's usual way to write it. And this phi I here some minus of the matrix, the Jacobian matrix of F1, Fk, no? Okay? So minus K by K, okay? And in the complement of phi I, so this open set Uy, okay? This is a cover of M star by Stein open sets, okay? Okay, M star is covered by this Stein open set, which the complement is, okay? And then I consider a form eta I defined Mi like that. This sigma I over phi I, no? Phi I. This sigma I is plus or minus 1, depending plus or minus 1, minus 1. And it's chosen in such a way that we have this, okay? When we multiply theta by eta I, we get this form, okay? So the points that when you consider in the intersection Mi, Mj, then we have this relation, eta I, the restriction of eta I to Mij equals to the restriction of eta j to Mij. And so we can extend these forms, there is some n form eta 0 on M star such that the restriction to each Mi is eta I. Well, so in this n form eta 0 is non-zero in all the points, okay, of M star. And in particular, if we take the n form mu1, this is some constant, no? Some constant times eta 0 bar. This constant is chosen in such a way that to get the good orientation, and there is an I to some power. So this, if we take this form, this is a volume form in M star, okay? This is a volume form M star. And this is the value of the constant C. And this volume form is used in the proof of theorem 1. And the idea is the following. The first step, there is another n form, eta, such that the Lie derivative, this x, this vector field x is the vector field for which is quasi-homogeneous, no? The surface, the variety is quasi-homogeneous. So for this vector field x, we have Lx of eta equals constant times eta, where this constant is trace of x minus the trace of u at 0. Then, if mu is the volume form, then we have this relation, no? Which comes from Lx. This here is big T instead of. But for T real, we have this relation for mu. So, okay, we have this relation for mu. So the the flow of the vector field, it is related. Acting in this form gives this result. Okay. So, for instance, if A is real, if real of A, real part of A, is bigger than 0, if you can imagine that if it is bigger than 0, then the volume is increasing when you t increases. Okay. And if it is less than 0, then the volume is decreasing, okay, of the surface. Okay, so you take the surface, small neighborhood of the origin surface, no? And then you saturate by the vector field a little bit, and then if A is bigger than 0, then the volume increases. But if A is less than 0, real of A, no, less than 0, the volume decreases. It's a contradiction. Okay. That's more or less the so, but the second step, so we consider the intersection of the M star with some ball, no? So one implies this relation. One implies that if real of A is less than or equal to 0, then the volume of the intersection of the ball with the surface is infinite, no? Okay? Because if it was finite, then it will decreases, no? With t, okay? It will increase with t, no? Increase with t, okay? And then the third step is to prove that if there is some map like that, then the volume with this form, no, is less than infinite. Okay, that's the idea. Okay, it's less than infinite. And this form eta 0 is a kind of volume form of M star. Is also used in the proof of theorem 2. If you remember, theorem 2 it says that in the case of it classifies in the case of n equals 2, k equals 1. No? Okay. And so the first step of the proof is to prove that the surface is quasi-homogeneous, okay, with respect to some vector field, okay. So the first step, there is lemma 2 here, no? So suppose you have a gem of at 0 C2 of a surface, the isolated singularity, and suppose that there exists a gem of a Lomov map like that, okay? Then the form eta 0 is exact, okay? But holomophically exact, no? Okay, holomophically exact, okay? And lemma 3 says that if you have the condition of lemma 2, okay, then M is equivalent to a gem of quasi-homogeneous surface, hypersurface, no? Okay, and then now the remaining part of the proof is to prove that once you have the surface the hypersurface is quasi-homogeneous, then it's not very difficult to find. So once we know that M is quasi-homogeneous, the idea is to use this corollary of theorem 1. Then by the corollary of theorem 1, if you have the eigenvalues the sum of eigenvalues must be bigger than 1, then this gives us the following, that if lambda 1, if we normalize like that, lambda 1 less than or equal lambda 2 less than or equal lambda 3, then the function which defines the hypersurface must satisfy these conditions. Okay? So that's the idea, more or less. Okay? And so once we know it satisfies these conditions, we can write like that and study case by case, and we get the forms in the theorem. Okay? But I have 1 hour, no? Okay. So particular, lemma 3 implies that the form eta 0 is a differential of some form where omega is holomorph, one form. And so is sufficient condition for M to be equivalent to a quasi-homogeneous surface if n equals 2 and k equals 1. Then, okay, so the idea is of the proof of theorem 2, no, is to find the first vector field to show that it is quasi-homogeneous, no? And okay, and then to study case by case. And this condition is also necessary in some cases. Okay? So the condition this means that if you have a quasi-homogeneous hypersurface, no, hypersurface, okay, and in the n-dimensional case, and suppose it's quasi-homogeneous with respect to this vector field, and then we have this comes from lemma 1 with and we have this relation here, okay, and then this implies that the form eta 0 satisfies this relation where A is trace of x minus 1. This x is normalized in such a way that x of f equals f, no? Therefore, if A is different from 0, then the form eta 0 is exact, okay? But if A is equal 0, then eta 0 is not exact, okay? Closer but not exact. And this is the case for this surface, for instance, okay? So in this case, the trace of the vector field is 1/3 plus 1/3 plus 1/3, is equals 1, minus 1 equals 0, okay? So, but, and this so except for this case, in all cases, the form eta 0 will be exact, okay? Except for the case of where a equals 0. And this corresponds to the following, more or less. Let me describe it. The vector field X, okay, it's tangent to the, and it's tangent and has a source at the origin, no? A source, okay, a repeller, no? At the origin. And the eigenvalues are rational. Then you can think about the quotient of the, say, m star by the orbits of the vector field. This is a Riemann surface, okay? And then the condition that the form eta 0 is not the omega in this case, that is means that this is this surface is elliptic, okay? This surface is elliptic, okay? In the other cases, the surface, so if A is different from 0, the surface is not elliptic, and in fact it's possible to determine to find the quotient in terms of the of A, in terms of A, okay? But let me so concerning Saito's theorem that I stated at the beginning, so my goal would be to find some conditions, some sufficient conditions, at least for the surface to be quasi-homogeneous. Okay, one well known is Saito's theorem. Okay, and that I stated before. But I have this small generalization that says that Saito's theorem, he says that the singularity is isolated. No? But here, I suppose instead that there is no smooth curve inside the singular set. Okay, inside the singular set. And then there exists a germ of holomorphic vector field which satisfies these relations. Okay, so in fact M will be quasi-homogeneous in the sense of existence of vector field. No? And Y is linearizable at 0. Okay, and in particular M is equivalent to the germ at 0 of a quasi-homogeneous hypersurface. Okay. Well, I will not give the idea. It's very simple, the idea of this theorem. Okay. And but so my goal would be to find conditions for the surface to be quasi-homogeneous. One condition is Saito's theorem. This is a small generalization. And so I would like to ask some problems relating to the theorems. No? So, for instance, in theorem 2, I have classified all possible surface in C3, no, is an isolated singularity, such that there exists a map from C2 0 to M0, no? So the same problem could be asked in bigger dimension, okay? But if you remember, we have theorem 3. For instance, theorem 3. Where is theorem 3? That says that for instance, there is no hypersurface in dimension bigger than, if n plus 1 is bigger than or equal to 4, there is no hypersurface isolated singularity which can be parameterized by C3, by Cn, no? Because the singular set should be of codimension, of dimension n minus 2 at least, no? Okay? That's the statement of theorem, okay? Of theorem 3, no? And so, but this is a question, no? Can one classify like I did in the case n equals 2, no? In C3, okay? In C3. And the proof, if you remember the proof in C3, I used that dimension 3 in the proof, essentially, in the proof that if you, where did I use it? I used in the proof that when the form eta equals is exact, no? Is d omega, then it is quasi-homogeneous. So the idea of the proof would be to find the vector field, the vector field, to find the vector field for which it is quasi-homogeneous, okay? And this vector field, in fact, is more or less like eta is d omega, no? So the form omega is a two form, no? And then omega is I is an interior product, no? The proof, yeah, I write here. So in the I write like that. Okay. So omega, the form eta is d omega, no? I said to you, no? Then omega is y, say x of eta in m star, no? M star, which in the case I consider is m minus 0, okay? And then the idea is to prove that this vector field, okay, the surface is quasi-homogeneous with respect to this vector field, okay? Let me say why. And if one can prove that, so that's the idea, no? But the motivation was that when the motivation was when we have a quasi-homogeneous hypersurface, the form eta, if you remember, if it satisfies some relation like that, no? Okay? Some relation like that, where A is the trace of something minus the trace of other thing, no? Okay? But this is okay? Well, the eta is 0, no? Because we are in the is a form with maximum holomorphic form with maximal dimension, no? Okay, the eta is 0, no? Then we have this. Okay, so if A is different from 0, then of course we have that eta is the A. So holomorphically exact, no? Okay, and the converse is true in dimension 3. So in dimension n equals 2, m contained in C3. The converse is true, meaning that this x here this condition here implies that this condition, the omega, implies in fact that it is quasi-homogeneous. Okay? So, the next problem would be, is it true that this condition, suppose we are in the case of complete intersection, we can define the form eta, etc., etc. And suppose that we have this condition. So, eta is holomorphically exact, okay? So the problem is that if this implies that M is quasi-homogeneous, okay? I know how to do for n equals 2, dimension 3, no? Essentially in C3. And I use C3, I use that, in fact, the idea of the proof is, first of all, to prove that the vector field x here, the vector field x here, he should satisfy. It is a vector field tangent to the surface, but it can be proved that x extends. I'll give you an idea. To a germ, to a vector field in a vector field, holomorph, in a neighborhood of 0, C3. It can be proved because the singularity is isolated. No? This is true in general. No, this is true in general. At least if the singularity has codimension 2, no? This is true in general, okay? But x extends to a neighborhood of 0. And let me call x again the extension, okay? Then since we have a singularity of the surface, no? This should be a singularity of the vector field, okay? This is a singularity of the vector field. And we can consider the trace of this. Well, this vector field satisfies something like x. F is the germ which defines the M, no? So it satisfies something like that because it is tangent to the surface, no? Okay? It satisfies something like that. So if h of 0 is different from 0, then we can divide x by h, consider the vector field y. So this vector field y satisfies, and then we use Saito's theorem, okay, in this case. So the problem is to show that h of 0 is different from 0. But it can be proved that this trace here is exactly h of 0 minus 1, okay? Can be shown this. So if h of 0, no, it's like that. If h of 0 is 0, then the trace is 1. In particular, the trace is different from 0. Okay? And then this vector field has some eigenvalue different from 0. Then the proof, the remaining part of the proof is to play back this and to show that, in fact, all the eigenvalues are different from 0. No, it's just to show that this implies if h of 0 is 0, implies that gives a contradiction, because this implies that the surface, the upper surface is smooth, and I have supposed it's not smooth. something like that, okay? So, but this, the proof, in the proof I use explicitly dimension 3, okay? I use to show that I use explicitly dimension 3, and so that's the problem. Second problem would be if this condition implies in general that the hypersurface is that is hypersurface is so in the case of hypersurface, no, is quasi-homogeneous. Okay. Okay. So in some cases, the fact that it's quasi-homogeneous implies this. We have seen, no? But in some cases not. But in this dimension n equals 2 in C3, then it's true, no? Okay. And the problem 3. Consider a germ of in Cn plus 1, no? And then give the more general condition on F in terms of its Jacobian ideal and its singular set, which implies that the germ of hypersurface is quasi-homogeneous. Okay? So Saito's theorem is an example of this, no? Of this. But certainly it's not the more general, because I state another theorem, no? A little bit more general, but in fact it's not so difficult to prove, no? Okay? But so give the more general condition. So the problem 4. In the case of surface, no? In the case of surface, isolated singularity. Every germ of holomorphic map, no, from C20 to M0, factorized through the universal cover, no? Okay. Remember that the maps found by Schwarz, no, that I mentioned at the beginning, they were the universal covering of the M star. Okay. So, but what happens in higher dimension? Okay. So, what happens is, if this is true also? If there exists a map, suppose there exists a map, then does it factorize through the universal covering? Okay. I think that one difficulty is that in dimension bigger, the singular set is at least of dimension n minus 2. Okay. In the case of hypersurface, singular set has big dimension. Okay. So we cannot suppose that the surface is isolated singularity. Okay. You cannot suppose it. So okay. So that's my talk. Thank you.
Any questions or comments?
Thank you.